And because we're all from linguistics and English language, I decided to add this little subtitle onto the main title with a focus on linguistics and English language, as that's where the case studies will be coming from. So I'm going to be starting off by talking in very general terms about quantitative and computational aspects of art research, and then we'll have two really great case studies from Fernanda and Henri. Their research uses quantitative methods and formal mathematical modelling to address substantive research questions in linguistics. And after that, we'll have a Q&A session and a discussion from the audience. Okay. So most of you are probably aware that researchers in art subjects such as linguistics and English language, literature, art history, and so on, haven't typically used statistical or quantitative methodology or drawn on computational techniques, preferring more qualitative or manual ways of doing things. But interest in these areas is on the increase, as is evidenced by things that have been happening in our disciplines. So just to give you some indication of this increase in interest, in this highly unscientific survey, as we can see here, in the Journal Victorian Literature and Culture, which was established in 1973, we find that 82% of articles using any of the words statistical, quantitative, computation or digital occur after 2000. So this seems to be a recent development in that particular journal. And furthermore, there's also been an increase in the availability of resources and tools in our area in terms of data sources, tools for data munging and tools for data analysis. For example, to explore our research questions, we can make use of a lot of digital resources available in different formats of raw texts, unannotated and annotated corpora, and we can also use things like social media, for instance, and social media like Twitter is really good for computational linguists who are interested in things like sentiment analysis and so on. Okay, so for example, here's an example of a digital text. It's called the Library of Latin Text. It's something I made extensive use of when I was doing my PhD. And this contains digitized text from textually reliable editions and starts off around about the period of the first records, round about 300 BC, up until Neo-Latin. And furthermore, this text archive is searchable. So, for example, here I've searched for the word est, and the examples appear in chronological order. And some of these resources, this resource, for example, is available by subscription, and you can get it through the University of Manchester library. But there are also lots of free texts available, such as, for example, the Latin Library online contains loads of free text which can be used for data analysis. But arts research needn't just be text-based. In linguistics and English language, for example, we've got a lot of experimental research going off, and we have ways of getting digital data out of this. So, for example, in psycholinguistics research, we might want to make use of the freely available PsychoPy, which can be used to present stimuli to participants, and we can record their reaction times to those stimuli. And in experimental phonetics and phonology, for instance, we might want to use ultrasound techniques to gather digital data about tongue positions. And then we have ways of wrangling and structuring these available data with automated tools such as Python. For example, in Python, the Beautiful Soup module allows us to scrape HTML documents from the web. This can be very useful, for instance, if the language we're working on doesn't have an available corpus. And NTLK, Natural Language Toolkit, and Pandas are also really useful for turning unstructured raw data into structured data sets. So, for example, if I wanted to extract all the words of a certain type, and for each extracted word I wanted, so in this example here, I've got an unstructured text, but but if I want to pull out various words, I can do that, and we can end up with this as an output where we have the word here, adjacent words, and some adjacent context on either side. So this is why I find Python really useful. And once we have our data, there are these sophisticated channels to quantitatively analyze it by using, for example, the programming language R. For instance, if you're interested in whether an author uses one word or another word when the two are practically synonymous, you might want to use some kind of classification technique to model the response as a function of various different kinds of predictors. And in that case, you'd want to use a classification technique such as logistic regression or classification trees if you wanted some kind of interpretable output. But if you're just interested in prediction, then you might want to use a black box like random forests or support vector machines, for example. And there are a variety of art subject-specific resources that teachers tell us how to use these tools. For example, in linguistics, we have things like Statistics for Linguistics with R by Stefan Gries, Quantitative Methods in Linguistics by Keith Johnson, and Analyzing Linguistic Data by Harold Byron. So these are really useful. But also in literature, we have this book that's recently just come out by Matthew Jockers called Text Analysis with R for Students of Literature. And this is very useful if you're interested in doing lots of computational text analysis for your research, in a sense to complement the close reading that you do in English literature and so on. And also we have relevant journals available to us to communicate this research. For example, the Journal of Quantitative Linguistics, and also this journal here, the Digital Scholarship in the Humanities, which was previously called Linguistic and Literary Computing. And university arts departments have a seminar series dedicated to quantitative enterprise in their particular subjects. For example, at the University of Cambridge, they have a seminar called the Quantitative History Seminar, and they also have one called the Digital Histories Seminar. So there's lots of going off here. And while we have this environment for good quantitative and computational research, in contrast to many other disciplines, disciplines in the arts haven't typically used these kinds of techniques, often relying solely on qualitative methods. So what I want to do now is to have Fernanda and Henri give their case studies to give you a taste of what kind of research can be done using these incredible tools that we have available.
Well, thank you. Thank you for the introduction. So I'm going to talk a little bit about my research, which has been focused on second language acquisition. So what we're going to see here is how a quantitative approach has helped me in order to make sense out of the data that I get. So, well, I would like to first explain what I'm doing. I think the main question is whether we all perceive sounds in the same way. Like, obviously the answer will differ if you have a different linguistic background. So some things that we can say about that is that speakers of a language have abstract representations of speech sounds. This is what we call phonemes in their minds, for instance, p, f, and so on. So we need these abstract representations in order to make sense out of the variation in terms of voice pitches, pronunciations, etc. So a sound like p will never be the same given that we have like different vocal tracts and different intonations and different linguistic background and so on. However, speakers of different languages have different phoneme inventories. So what we know is that, for instance, Spanish speakers, like native speakers of Spanish, like myself, do not have the vowel that English speakers have in the word cut, for instance. Like we don't have that. We have something similar, will be a. a very different. It's very different if you look at like in a spectrogram, for instance. But if you just listen to it, it's like, well, that's kind of the same thing, right? Another example: speakers of French, for instance, have this uvular fricative sound, the famous French R, like the R sound, that speakers of English do not have. Speakers of Spanish don't have it either, and so on. So why is this important? Well, if my native language, my L1, has phonemes that the second language doesn't, then two things are going to happen. The first one is that I will automatically try to categorize that sound into any of the sound categories of my native language. So I'll try to interpret that sound that I hear from a speaker of my second language, and I will try to pass it through the sieve of my native language, right? If two non-native sounds, however, are categorized as members of the same native sound category, then they will be perceived as realizations of the same phoneme, right? So, for instance, a word like caught and a word like cut are going to be perceived as the same by speakers of Spanish. Like, it's exactly the same thing. Even though a native speaker of English will be able to tell, no, that's absolutely not true. Same thing with speakers of Japanese trying to find the difference between rock and lock, right? Because they don't have that distinction between these two phonemes. So the question is, can we learn how to perceive like native speakers, like in the case that we are a non-native speaker? And in order to go to the research that I'm doing, like in particular, I'm working with the perception of English vowels by speakers of Spanish as a first language, right? So while Spanish only has 5 constant monophthong vowels, which are the ones in black, English can even double this number, right? So it could be like much more vowels. I'm just like considering those of General American English, but it will depend on the dialect. So that's an even further complication that we have to deal with. So some English vowels will fall in the boundary between these two native category areas in the acoustic space. So that makes a lot of, that poses a problem for us. So next one. So advanced L2 speakers of English must create new sound categories by splitting the ones that they already have. However, we want to know whether this is possible or not, right? So for this to happen, then 2 assumptions must be made. The first one is that the non-native speakers have to realize that there is a difference between the 2 sounds, which is kind of difficult because we already think that they're the same. And they need to add a certain new parameter in order to create a new boundary in the perceptual space. So it will be something like, well, this is a, and these are like 2 different types of a, so they're like slightly different, but I can't exactly describe how different they are, but they are kind of different, or maybe not, and so on. So it's a really complicated stuff for the non-native speaker. And there is no other way to know this than via experimentation, right? So here's where the quant part begins. So, well, of these 3 experiments, I will only have to show the first 2 because I think we're going to run out of time if we try the 3 of them. So let's see experiment 1. So if a non-native speaker has a possible yet not real English-like word with an English vowel, let's say the vowel in cut, so will the vowel be categorized in the same way, sorry about the typo, that if it's encountered in a Spanish-like word? So for instance, if this vowel was inserted in a nonsense word like puck, will this be perceived as the same sound if I embed it in a word like gan or tar and so on, which will be like more Spanish sounds, more Spanish sounding words? So, well, let's run an experiment then. So we ran an experiment with 42 native speakers of Spanish, beginner and advanced. They had to do a forced choice categorization test. So they were asked to say, to tell whether the vowel that they were listening to was like either one of the 5 Spanish vowels that they have. The stimuli were CV nonce words, CVC, sorry, which is consonant vowel consonant, and so on, right? So it was a somewhat like okay sounding word in either Spanish or English. And V was like one of these boundary vowels, right? The ones that are in the boundaries of the native categories. So something like the vowel in cut, which will be in the boundary between native Spanish A and native Spanish O, like somewhere in that gray area. And in order to compare both English and Spanish vowels, we created a set of nouns words with Spanish vowels as well. So this is what the vowels will look like in the perceptual space, right? We know that vowels are can be described acoustically by form and frequency. So that's what the chart shows. So what were the results? And this is where the interesting part begins, right? So we run the test, right, and we have different results, right? So if the vowel of right, the one in bed, that is not in Spanish either, we have something like more tense, like then we will be able to find a certain difference between the two groups, right? Whether they were inserted in an English-like nouns word or in a Spanish-like nouns word. There seems to be no difference, right? It's a very small difference. So let's say that there is none. Let's see the next one. But what happens here? That we have a different distribution of the categorization. So tokens of this vowel were categorized in different ways, depending on whether it was inserted in an English-like environment or a Spanish-like environment. But how significant? And that's where quant methods are very important, right? So the only way to know whether this variation is really important, is really significant, and we can say yes, there is a strong correlation between the type of environment where the vowel is inserted or whether it's not, right? In terms of how it's being interpreted, then the only way to do it is via running a stat test, right? So the simplest one, the easiest one, is the chi-square test. They will tell us whether this is not just a random distribution, right? If there is any logic behind. And furthermore, we can run a generalized linear model test, which will also give us a clue, and it will pinpoint exactly which one of these is going to be the most important response according to the data that we have. The following one is the vowel E, which is in the word kit, for instance, which we don't have either. We have either E, a very tense E, or an E. And here things become a little trickier, right? The first one didn't seem to be there didn't seem to be a difference at all. The second one, there seemed to be a huge difference. But what about that, right? It's yeah, there is difference, but we don't know exactly how much. So again, we need to run certain statistical tests. Right, so that was the first experiment, and then experiment 2. The research question was whether if we built a 7-step continuum between two non-native vowels, right? For instance, the vowel in the word cut and the vowel in the word, what could be that? Lot, for instance. Will then non-native speakers be able to find a boundary in the same zone where native speakers will find it, right? There would be a moment in which we'll be able to say, okay, this is the vowel in cut and this is the vowel in caught, for instance, and so on. So we wanted to know where exactly in this 7-step continuum will the native speakers find a boundary, and where the non-native speakers will find a boundary, if they find a boundary at all. The methodology was similar. We have native speakers of Spanish of different proficiency levels, and a control group of 7 native speakers. So we used the forced choice categorization. The subject was asked to tell whether the two stimuli were the same or different. And the stimuli were a pair of vowels, sorry, where vowel 1 was a token from a 7-step continuum, and the other one was either one of the endpoints of this continuum. So, and we added an interstimulus interval of 1 second between vowel 1 and vowel 2. That's how the stimuli look like. So some Spanish vowels we consider as well. This is part of a bigger experiment, and some of the English vowels too. So we had to use Pratt, right, one of the most important phonetics software, which is also open source, so it's very good. Allowed me to synthesize these vowels that are in between, in equal steps. So results can show will show something like this, right? So if we compare something between an continuum then we will have like the first one here, right, compared against itself. People will say, okay, this is the same, right? And as we can see, most subjects say that, yes, this is the same vowel. And here there will be like complete different vowels. So we were expecting them to say, yes, these are like complete different vowels. However, we can see that if we count the amount of people saying, perceiving these two vowels as different, will differ whether they are native speakers, whether they are advanced speakers, or just beginners, right? So the black line are native speakers, the blue line is the advanced, and the red line represents the beginners. So we can see that the discrimination curve is different, right? But again, the question is how different? Like, can we say that this is significant? And whereas in other cases, like in this other continuum that we built between the vowel in the word that would be foot, for instance, versus the vowel in kit, how different are they and how similar are they? Like, they seem to be very similar, but again, are they similar enough? So these are questions that that a quantitative approach will be able to answer in a much precise way, right? So in order to wrap up, how do we make sense out of the data? So in experiment 1, we can see that the experiment collects data on categorical variables, right, which are collected from the real world, which at the same time has a lot of noise. So we have to make sure that whenever we say something, there will be statistical tests that will tell us, like, yes, there is a certain amount of noise, right, a certain amount of variation in the results that can be attributed to noise, but we will like take that into account in order to tell whether this is like important, significant, or not significant. So experiment 1, the simplest test that we can run is the chi-square test. And the generalized linear model will allow us to pinpoint the response that is most sensitive to this among all this pool of choices. And as for experiment 2, if we consider that the native speakers data is the right kind of response, then we can run a signal to noise test. So you can tell that if you just like calculate the differences between one response and the other, and you just like get through by an equation how much sensitivity there is in a certain towards a certain stimuli in each one of the groups that we have tested. On the other hand, if we just want to know how different these curves are, then we can run another statistical test, Kolmogorov-Smirnov test, that will give us a p-value. And additionally, we can also run an ANOVA, which will help us to analyze the spline if we want to smooth the curves, and so on. So every test will allow us to give a different answer, a different perspective from which the data can be analyzed. So yeah, that's what we have done so far.
I'm focusing on another way in which language changes, namely on a population level. So it's a fact that languages change during their histories. For instance, if you think about English, English syntax, then for instance the way you form a question in modern day English is using something known as do support. So you ask things like, do you like ice cream? And so on. Whereas in earlier forms of English, the equivalent question would have been, like you ice cream. Similarly, negation is facilitated by do support. So you might answer, no, I do not like ice cream. Whereas in Old English, you would have said something like, I like not ice cream. Or actually, that's for Middle English rather than Old English. Anyway, languages change on many levels, and I've been looking at different ways of applying mathematical models to explain these processes of change, which could be syntactic changes, they could be sound changes, something like the cut vowel starting very high, as in kot, and then becoming kot, and so on, over time, over generations of speakers. Right. The most general kinds of questions that we can ask are these ones here. Why do languages change? How do they change? Why does a linguistic innovation arise? Why does do support, for instance, arise in the history of English? And then when you have that innovatory variant, how does it propagate through an entire speech community? Also, what language internal reasons are there for change, and what kinds of language external reasons are there? And can we tease them apart? Now, in this talk, I'll be focusing on a very, very specific question, which is, can language change be neutral? And I'll approach this question from the point of view of mathematical modeling and computer simulations of language change. Now, in many cases, it seems clear that languages change because of some reasons, right? So, for instance, it may be some consonant may be difficult to pronounce, just for purely anatomical reasons of the vocal tract, and then we can state that as a reason for the disappearance of this consonant from the language over time, or of its replacement with something different. There may be cognitive reasons for change. There may be social reasons. So there is this idea of prestige, whereby you say that a linguistic innovation is adopted by people because people consider that it has social prestige, and then the conventional variant dies out, and so on. On the other hand, it's equally possible that not all changes are motivated by factors such as these. And this is the so-called neutrality hypothesis, which has been suggested in the literature, but hasn't really been tested very thoroughly. Let's move on, thank you. Okay, so this is how I define neutrality. The probability with which a speaker acquires a certain linguistic variant out of a number of competing variants equals the relative frequency of that variant in the speaker's linguistic neighborhood, modulo a small probability of innovating uniformly at random another variant from among all biologically possible variants. Now that sounds a bit complicated, but it really isn't. If you think of yourself as a speaker immersed in a language community, then what this says is that the linguistic variant that you end up using is directly proportional, or let's put it this way, the probability of acquiring a certain variant is exactly the frequency of that variant in your environment. So the more people use, let's say, a certain kind of vowel, the more likely you are also to use that vowel. And there are no biasing factors which would bias you to adopt one vowel or another. So it's purely frequency dependent, with the important proviso, though, that there is some noise in the system. So there is some small probability of innovating something which doesn't exist in your community. Okay, so can this sort of thing happen? That's the question. Previous literature shows, modeling work shows that neutral change isn't really to be expected in certain cases. James, thank you. First of all, if your population is a so-called well-mixing population, this just means that all the speakers in your community come into contact with all the other speakers. So you have a social network like this where those little dots represent individual speakers, and then everyone is connected to everyone else. This is a well-mixing population, and we have modeling work that demonstrates that in these kinds of situations you don't get neutral change. There always has to be some sort of biasing factor that motivates change. The other possibility is that of a structured population. Now here, the population can be either static or dynamic. And by static population, I mean basically a social network which is invariant in time. It doesn't change over time. So let's say that you are this guy here, and you have 3 friends somewhere here in the network. If the population is static, then that means that you never lose those 3 friends, and you never get new friends. In a dynamic network, on the other hand, that sort of thing can happen. Now, here we have a big question mark, because this question hasn't been explored in the context of a structured and dynamic population. And that's the idea. That's the purpose of this study. So here I assume a very simple social network that represents a speech community. It has some number n, that's just a variable to stand for some number of speakers, and each one of those speakers will entertain one of several possible linguistic variants. For instance, a certain pronunciation of a certain phoneme, or a certain syntactic rule in their grammar, and so on. Now, to make this network dynamic, I assume a certain kind of algorithm that rewires the network over time. I won't go into the details of this in the interest of time constraints. The important thing is that there is a parameter in the model, this sigma here, which controls how clustered the network becomes. So your network can be either very sparse and everyone is sort of loosely connected, or your network can be very clustered or clusterized, in which case you have a group of influential speakers in the network who are connected to many, many other speakers. That's basically what the sigma parameter controls. If sigma is very high, we get clustered networks. If sigma is low, we get random networks. And I assume that at fixed time intervals, people are removed from the network and added to the network. And then the sigma parameter allows us to control how people are given their particular connections in the network. And then variant adoption is supposed to happen on purely frequency-dependent grounds, as the neutrality hypothesis demands. Just to illustrate how this works, now this is a toy network, very small. Each of those dots represents one speaker, and the speakers can be either green or purple. If they are green, then let's say that they say things like cut. If they are purple, they say things like cot or quote. I don't have that vowel, so that Mancunian vowel, but it's somewhere up there. Cot. All right, let's move on. So at every iteration of this model, we pick one speaker, we remove them, and introduce a new one. And there are these model parameters, I won't go into the details, that control the number of connections given and the probability of connecting in certain ways. So we give new connections, in this case 4 of them, one by one, yes. Those are the 4 friends that the new still blank or white speaker gets. And then variant acquisition happens. Now if acquisition or adoption is frequency dependent, then the probability of this guy ending up purple should be 3 per 4, in other words 0.75, because he has or she has 3 purple friends, and the probability of becoming green should be 1 over 4. So in this case it's probable that they end up purple. So in the end we have change. Basically this node in the network has changed from being green into being purple, and the connectivity pattern of the network has also changed. So this is the basic operating principle behind this particular model. And with tweaking these model parameters, we can generate different kinds of networks. Really the only important thing here is that networks which are in the top left corner are very random, and they are not clusterized around a central component of influential speakers. whereas networks to the networks in the bottom right corner have this sort of tight clustering. All right. Now that we've defined this mathematical model, we can actually ask: does it give us neutral change? And also, if change happens, what kinds of trajectories do we get? That's also very important from a model evaluation point of view, as I will demonstrate in a moment. To answer these questions, I'll define 3 criteria that any model of change should satisfy. The first of them is dominance, which simply states that for most time, there is one of the linguistic variants dominates. So all the speakers, or at least most of them, speak that variant. The second criterion, shifting, says that dominance notwithstanding, we need to have periods of change where the community shifts from dominance by a certain variant into dominance by another variant. And finally, there is a slightly trickier condition of monotonicity, which basically says that these change processes should be smooth. Do we have a whiteboard marker? Probably not. Anyhow, if you were to plot the frequency of the innovatory variant against time, if time is on the x-axis and the frequency is on the y-axis, then the frequency should go up along a smooth curve. It should not do something like this, because that's not what we see in actual historical data. And monotonicity is designed to measure that. Now, this is one particular run of the model. Here we have 3 competing linguistic variants, red, green, and blue. And we see that there is change from blue dominance to green dominance. So here, the relative frequency of the blue variant is 1 in the community, so everyone uses that. But then the speakers are replaced, and this network rewiring algorithm operates, and finally we get change from blue dominance to green dominance. However, this is not a smooth change because of all that jagging motion that we see. This is another example, another history from generated using exactly the same model, but with a clustered network. And we see that there is change from red dominance to blue dominance, but the change is very, very smooth in comparison to what you saw in the previous plots. Now we can quantify all of this. I won't go into the mathematical details. Let's just look at the next figure, this one here. This essentially gives the probability of change in different kinds of social networks. Recall this sigma parameter. It basically controls the clusterization of the network. When sigma is close to 1, we have a clustered network, so very influential speakers in the center of the network who are connected to almost everyone else. If sigma is 0, the network is more random. And we see that the probability of shifting or changing increases when clusterization increases. This mu parameter here controls the rate of innovations that happen. It also plays an effect here. We can also look at the other 2 criteria, dominance and monotonicity, which can also be quantified. And basically, what we see is that there is a sweet region here somewhere where both of those measures get high values as we'd like them to have. And finally, we can put all of these measures together to find this particular model parameter region where neutral shifting is reliably observed and it's also smooth or monotonic. So to wrap this up, the question was, is neutral change possible? My answer is it's possible if your language community has a certain kind of structure and dynamics. There are further results into which I can't go here. I'll just show, let's fast forward a few slides. We can, not quite so much. And yes, this is the one. So to me personally, the real value of doing these things mathematically or computationally is that we can actually prove mathematical facts about these models. So something like this is actually a theorem that follows from the first principles of the model, and we can actually prove what is the exact probability of an innovation propagating across a network. Okay, I think that's more than enough.
Great.
We want to
Thanks
wrap it up.
ever so much, Henri.